All right, well, I think we're ready to get started. Hello, everyone. My name's Marty. Most of you have met me at least briefly. I work for the Australian Ocean Data Network, which is, I guess, essentially the data center for the Integrated Marine Observing System, or IMOS, which is Australia's national ocean observing facility, I guess. And so I work on providing access to data that IMOS collects, and increasingly other sources in Australia, and helping people to get access to the data and to use the data. So I'm going to talk about different ways to access not only our data, but in general data related to oceans, and not just oceans specifically, but generally environmental and geographic data, and more specifically accessing them remotely using a range of different methods, some old, some newer. And I'm going to use examples or example data from IMOS. And just something to note, in this notebook, we're actually, I'm always going to just give you a direct link to the data set. So in case you might wonder where that comes from, there is a way to actually browse and discover these data sets. And we have the AODN portal. There's a link to it on this slide, where you can interactively browse and search for and preview data sets. We have a metadata catalog and a thread server, all of which allow you to discover some of these data sets in different ways. Just on a practical note as well, I'm skipping many of the cells in the notebook that you're looking at. So just to keep the slides a bit clean, but I encourage you to follow along on your own screens in the full notebook. Then you'll see all the code as well. There is also, I might as well mention that now there's some optional code cells that have been commented out, which access a local copy of the data that we've preloaded on here on the Jupyter Hub, just in case there's any issues with everyone hitting the same server with exactly the same request at the same time. Then that might, hopefully won't, but might cause issues. All right. So firstly, to motivate while we're talking about remote access, well, the old way, the sort of original way, I guess, that people would work with data is to have it sitting on their local hard drive, basically, whether it's their own data they collected or they downloaded it from somewhere else, and you can access it and work with it perfectly fine from there. And that's still a reasonable thing to do in many cases, and it works fine, but there can be various issues with that. For example, as you're probably aware, data sets are getting quite big these days, and sometimes they might not fit on your hard disk in the first place. You might only want a small fraction of the data, but you need to interact with and sort of query the full data set initially to actually extract the bits you want. It might actually be coming from somewhere else where it's routinely updated, and you want to also make sure you've always got the most up-to-date version. So various things like that, which mean that these days, increasingly, it's more convenient to have the data managed in a central location, often in the cloud, and then have your code access it directly from there. So in this tutorial, we're looking at different ways we can do that. Some of the common ones, and I'll mention some of the newer ones that are emerging these days. So one that's been around for quite a while and is quite common in some areas, I suppose, is OpenDAP. It's a protocol that allows you to talk to a data set over the web and look at its metadata and access a subset without downloading the entire file. It's loosely based around the NetCDF data model. Hopefully you're familiar with NetCDF as a format. And in fact, the advantage is that many tools that talk to NetCDF files can simply also can actually accept an OpenDAP URL directly and talk to it directly as if it was a local file. But in the background, only fetching the subsets of the data that it needs to. So this is the case in Python, where our favorite tool to work with NetCDF data, Xarray, can simply handle an OpenDAP URL and open it as a dataset object. So we're going to look at an example that we access through the AODN thread server. And here's the URL. Sorry, the longer lines of code get chopped off here, but you'll see the full code in the notebook. Just one thing to note here, this is one we're going to open directly through the code, but you can also, there is a web interface to OpenDAP. So if you just take this same URL and add .html on the end, you get a link that you can put in your browser, and you can preview the metadata there. You get it's actually a web form where you can also pick specific variables from the data set and even index ranges and download the data from there. Once we've got that URL, we can simply get Xarray to open the data set, and from there on, it's the same as working with a local NetCDF file, essentially. You can see the coordinates in the file, the variables, all the metadata. We can look at individual attributes in the file. And in this case, the example we're looking at is a depth gridded time series product derived from moored temperature recordings at a site near Sydney. There's a link for more info if you're interested. And from there on, we can just work with it as if it's as any Xarray data set. We can do some nice plotting here. I'm using the HoloViews and HVplot interface here, which is a slightly nicer version of the original plotting, sort of basic plotting that Xarray allows. By the way, one of the slides I've hidden is all the imports, but you can see that in the notebook. So we're just pulling out this product has a 13 years worth of data, and we're just pulling out 1 year's worth in here and plotting it as a two-dimensional depth versus time, and the color showing the temperature here. And by the way, one thing that this HoloViews plot allows you to do is do this interactively. So I've got a commented out set, well, a cell in there that you can comment out, which turns this back into interactive plots. And then you can zoom in and out and click on things in the plot. Also, I guess I'm talking about Xarray here. I'm assuming most people are familiar with that. If not, I think it'll be covered. It might be covered somewhere in the program, or has been covered, hopefully. Even if not in this year's program, there's definitely some in previous years' tutorials. So look for that if you need to. can do. And I might pause here and give you a bit of time if you want to have a run through on your version on your notebook. Okay, so now that we've had a play with OpenDAP, let's have a look at another one that's not a new way. It's been around for a while. This is the Open Geospatial Consortium standard for web feature service, which is specifically designed for tabular data to be accessed via the web. And so in this context, a feature is essentially a row in a table with a bunch of data in different columns, a bunch of properties, but also what's called a geometry, I guess, or what tells you what geographic location, point, or area that data refers to. And so those two together make up a feature, and a collection of those features is what makes up a table for a web feature service. So WFS allows you to access a table like this remotely and filter it based on both the geometry and also the specific properties within each feature. And in Python, a library called OWSLib to access not just WFS, but other standard web services defined by the OGC. So as it turns out, most of the tabular data that we are hosting here at the AODN is available via WFS. And you can get to it here. You can connect to this server that serves up all these different tables, and you can list all the different what WFS calls a feature type, so a table, a particular type of table or a data set. And as you can see, they've got nearly 400 distinct data sets available. Now, these short names here probably don't mean much by just looking at them like this, but this is why we maintain a metadata catalog, which then links back to, it has more info about each of the data sets and then links to individual ones of these, which you can then access. So we might come back to that at the end and show you how you can find those. But for now, let's assume that we already know which feature type we want. And in this example, we're going to look at some CTD profiles that are obtained at some of the national reference stations around Australia and some other sites around the country. So we put in this type name and provide it to this WFS object that we've created, and we can look at the properties that are available in this data set. So it's a list of the names of each column and their types. And we can specify a subset using a geographic bounding box. So here we're going to do that, provide a bounding box, and we're just going to limit it to 10 features, so 10 rows, just to get a quick preview of the table, and we'll get the result in CSV. This does allow for a couple of different formats, such as JSON. But CSV is easy to open then as a pandas data frame, so we're going to do that, and straight away we can look at the table. There's a lot of rows in here. We can also get the So we can get a subset based on values in specified properties or columns in the data. And we can build a filter like this in a fairly Pythonic way, even though in the end it needs to be turned into XML, but we can just set individual properties. So here we're going to use this site code parameter to say I just want data related to this one site, which happens to be a mooring at Port Hacking just outside Sydney. And we're going to use filters on these quality control properties to extract only the ones that have been labeled as good data by automated quality control procedures. We can also limit what properties we want returned. As you saw in the previous slide, there's quite a few different columns in this data set, but we may not actually want to download all of them. We might not be interested in all of them. So there's no need to get more than what you want. So that's why we list these property names here. And then again, we get the result as a CSV and get a data frame. Now we've got a nice, neat little table. And we can then plot things like profiles. Here we've got the profile, the same profiles. This is all of the profiles at that site for temperature, salinity, and chlorophyll concentration. Or we can do a number of different things. Anything really that we can do with a pandas data frame at this point. And just for something interesting, since this is now looking at the same site as the data we looked at in the opened up example, which was from the mooring, we can now extract the temperatures from these CTD profiles at a depth of say 20 meters and compare to what we saw in the mooring over that same time period. And if you did this, well, this is the entire span, so it's a bit hard to see, but if you did this with the interactive plots and zoomed right in, you can see there's a pretty good agreement, which is good to know. And that's that example. If you want to have a play with that or ask any questions, we might pause there again for a couple of minutes. All right, shall we move on? So the next section I'll be talking about accessing files directly on cloud storage. So these days, a lot of data sets are being stored in cloud storage, such as Amazon's Simple Storage Service or similar ones from Google or Microsoft. And if they're set up for public access, you can just point your code directly at a URL again and access the data from there. So again, I'll use IMOS data as an example, which you can access via, which is stored, all the public data stored on an Amazon S3 storage bucket. So to talk to that, we use in Python, we use the S3FS library, which basically makes it look like a local file system, or you can interact with it in a very similar way to a local file system. There's a link where you can actually just browse the contents of this bucket directly. Oh, sorry, that's the description of what an S3 bucket is. And what we'll look at in this example is high resolution surface temperature product, gridded product created from satellite and in situ observations. And it's stored as a collection of daily gridded netcdf files on this S3 storage. So we create an object to talk to the S3 bucket, and we use anonymous access here because it's openly accessible. So we don't need to do any sort of authentication. And we get a path here which starts with the name of the bucket. And then the rest of it is a path hierarchy, or actually what's called a prefix for a S3 address. But we just use a list command that would be very familiar from working on the command line in Linux, to list a bunch of files. So here are these daily files, netcdf files. And then we can just pick one, in this case, the most recent one, and we have to use this sort of as an intermediate step. We need to open it with this S3 library, but then pass that directly into Open Dataset with Xarray, and then as before, it just becomes a dataset that we work with using Xarray. And then we can just pick a variable, in this case, this analyzed SST variable, and take a small subset and plot an image of it. In this case, there's a few intermediate steps because we're using this. This is another package in the sort of HoloViews ecosystem, I guess, called GeoViews, which is for working with maps and geographical data. So we just have to do another transformation to that sort of data set, and then we can plot it like that. I think you could actually do a very similar plot in a simpler way with just Xarray. I probably could have made this a bit simpler, but there it is anyway. This allowed me to put a nice little overlay of showing where the land is. There are many other packages that you can do this sort of thing with as well. So I just wanted to go into a bit of detail about what's happening here, because this is actually going to, well, it'll motivate the next bit. But what we've done is we've opened one file that sits in this S3 bucket, but we've only actually made use of the metadata, or directly actually accessed the metadata from the file and one of the 4 variables that are in there, along with the associated coordinates. So if the file was on a local file system, you could, your software could easily just read those specific bits out of the file. However, because of the nature of these cloud storage services, such as S3, which are also called object storage, they work on the idea of an object, which is an entire file, which you can put in and pull out as the basic operations. And so you'd essentially have to still pull out the entire file before you can start accessing bits of it. I do have a little footnote saying actually technically you can access byte range, I guess, within an object, but that's sort of more advanced usage that requires extra work anyway. So for this case, essentially what's happening is, even though we're accessing a part of the file remotely, it is being downloaded from the S3 storage in the background. And this can be an issue if you're accessing just a small part of a large data set in a large file. Obviously, it's not a very efficient way to work. So just to push that a bit further as an example, let's say we have this data set that consists of whole maps or in the Australian region of this satellite surface temperature, but we actually want to drill down at one point and extract a time series. Then you'd have to still pull out each file, each complete map, just to extract one value from each one. And we're going to do this as a demo. And Xarray has this handy function called Open MF dataset, which stands for multi-file dataset. So we can create a list of objects. So in this case, we'll create just the past month, so July's maps of this surface temperature product, and then pass that in. So we're opening basically 30 objects in the object store at once, and Xarray does a pretty nice job of it. And note now, if you can see that in this slide, we now have, along with the latitude and longitude grid, we now have 30 time points in our data set. So it still just looks like a single data set, but in the background, it's actually open 30 netcdf files. And note that it's wherever I actually ran this last, it took 15 seconds to do this, even though at this point, all we've really looked at is metadata from the data set. And there's probably some lag involved with accessing a remote server as well, but I think part of that is just the fact that it had to actually pull out every file, every one of those files. The other note here is that the variables in this file, it's not actually very easy to see in this view. So they're still at this point only opened as this Dask array, so it's not actually loaded the data into memory. It's just keeping track of, okay, there's an array where the data exists somewhere, and here's how I know it's going to get it when I need it, and here's how it's broken up into these chunks. In this case, each file is a complete chunk. Okay, and then I've put in another example where we've got, again, there's those exact same files, same netcdf files sitting locally on this Jupyter hub, and open them from there with the same MF dataset function. And in this case, it still took a little while, but it's only 5 seconds, so it's quicker. And possibly some of the difference is actually due to not having to access or read the entire file. But whichever way you do that, in the end, you've got an Xarray data set. And when you actually ask it to do something, such as plot these values at, so here we've done this pixel drill, this extracting a time series, it'll then go and pull out those values. So have a go with that. There are, as you might have suspected, the next thing I'm going to say, there are data formats specifically optimized for storage, for cloud storage and for access, to basically overcome these limitations that we just saw with netcdf. And for, I guess, what would replace netcdf for multidimensional array data is a format called ZAR. So that was specifically developed for efficient access to such a data in the cloud. And the way it does that is by breaking up each array into small chunks, and storing each one in a well-organized way in individual smaller files or objects on this object store, so that you only need to access the bits that you want, and also the metadata, both about how the data are structured, as well as any other associated metadata, are stored in, again, separate files that you can read without having to touch any of the data. So it makes for more efficient access to those data. So what's called a ZAR store. So it's really this hierarchy of directories with all the different chunks and associated metadata. Again, it can be easily, such a store can easily be opened using Xarray. And in this case, we've actually got a dedicated function called OpenZAR. Although I think Open Dataset can also handle it, you just have to specify the engine to be able to get it right. So in this, in here we've got a different data set, which I noted in here. This is we don't actually currently have any production data yet that's in ZAR format. That's coming. We're working towards that, but we currently have this experimental data set, which will be there for the near future, but one day it might be gone. So it's a collection of still satellite data. It's not exactly the same product that we were looking at before. And so we point our S3 file system at this path here, which is a year's worth of this satellite product. And then in this case, we just open it as a data set. And notice here we can see it's quite a large, relatively large long grid just for the region around Australia, and it's got 178 time steps in it. And again, we see all these Dask arrays, which mean that it hasn't actually loaded any data at this point. It's just read the metadata. It knows what size all the arrays are. And it also knows these chunk sizes. So it knows how big each chunk in this case is 64 time steps by 64 steps in latitude by 64 steps in longitude. And we can look at the structure of an individual variable, and it shows you how the entire three-dimensional array is made up of lots of these little 64 square cubes. And in fact, as we'll see in a minute, this is probably not optimal. And a hint to that might be that it's showing that when you ask Dask to do something with this entire array, say you want it to compute this entire array, it's got 20,000 chunks to deal with, which is quite a lot. What that means in practice is if you actually get it to do some sort of computation, each of those chunks is an individual task that needs to be managed with its intermediate results to keep track of and passed on to the next bit and so on. So it gets quite complex. This is what Dask does, but I think it tends to struggle sometimes when you get too many tasks. So we're going to try and plot again a subset of this data set. We're just picking out really quite a small subset. So we've got a year's worth of data. We're just going to pick out one day. These are daily files. And again, we're even narrowing down the latitude longitude range a bit and just picking out the sea surface temperature variable. And I actually, oops, I don't actually have the plot in there. But let's see how you go running that. There were times when I had trouble, it can take a couple of minutes to load. And I think that's because it's got too many chunks, but we'll see if we can get it to actually work. So it's not I guess what I'm saying is, in this case, the way the data set is chunked is probably not optimal for this this use case that we're trying to do, which is plot a map. It was actually designed more for doing the time series plot that we did before. So have a go at that. Yep. So okay, so that's a quick intro to ZAR, and then going back to tabular data, the equivalent cloud optimized format for tabular data is well, one of them that's getting quite popular, I guess, is Parquet. So again, this does the same sort of thing as ZAR does, in that it breaks up the data set into smaller bits. In this case, each column in a table is stored in a separate file or object, and the columns themselves can be further partitioned. If there's many rows, they can be partitioned into what it calls row groups. So again, the idea is, if you only want a subset of the data, you can get away with reading only some of the files associated with the complete data set. So I'm borrowing here a quick demo that Denise might be familiar with. So there's a really nice notebook that I'm linking to there that looks at some temperature logger data from the Australian Institute of Marine Science. So it's a data set containing 150 million temperature measurements from sites around Australia, and in a single Parquet data set. And we're going to use, in this case, the dask.data frame library or object to access the Parquet data. And again, as we've mentioned with Dask, the idea is that it does things in a lazy way, which means it only reads things, only reads the bits that are necessary, and only when it's necessary. So there's the path to this particular data set, and in this case, I noticed that there's actually some temperature loggers in there that are not far from where we are here in Dunsborough, Western Australia. So I've narrowed it down to a box around this region, and we can specify what columns we want, and I just shortcut to just putting them in. If you want to look a bit more into that data set, have a look at that full notebook. This data set stored in an S3 bucket, and we can access it anonymously, so without any authentication. And we load this directly into this Dask data frame, which looks very much like a Pandas data frame. Works the same way essentially in terms of the interface. And what we've got now is a bunch of timestamps and a site name and this quality control value of temperature. We've got what we're left with after, given we've filtered it on as we read in. Out of that 150 million rows, we've only got just under 100,000. So that small enough subset that we can actually now say to Dask, let's just read that into memory. And so at this point, this turns it into a regular data frame. And then we can look at, for example, okay, what sites are there in there? Here are the 3 sites that fit into that bounding box that I created. and then we can just plot all three of them in different colors. And there they are. And that's a very quick example of talking to a Parquet file. Wrap up. Okay, so those were the ones that I managed to find examples of or create examples of. There are many others, or other ways, or numerous other ways to access data. So ERDAP is another online sort of web access facility that allows searching and subsetting and downloading data sets. And one of its advantages, I think, is that it provides a whole lot of different output formats. I don't know much about ERDAP, but I've given you a link to an example, and I also note that in last year there was a tutorial that covered that. Then sort of newer ways of doing things. So I mentioned web feature service in this tutorial. The same. So from the Open Geospatial Consortium, there are now newer standards for these APIs, these ways to interact with data sets. One is just called features, which is essentially a replacement for WFS, and then there's coverages, which is more for I guess geographic gridded data. And then the older version of that, not quite the same thing. No, there is a web coverage service, which was the older version. The other one is web map service that which is again interacting with geographically gridded data, but it gives you map tiles. Basically, it renders map tiles, so images. And again, there's an example from last year's tutorial, and it's gone off the page, but I've added some additional links that are helpful for more notebooks that are worth looking at, and good examples there. And that's all from me. If there's any more questions.
Oh, it's just some clapping on the platform.
Thank you.
Would you like to show the portal?
Portal, yes. Yeah, I'll go through that quickly. So I'll go back to my first slide. Or actually, this one. Yeah, so I mentioned the AODN portal. Let's go to that. So this is our web interface to all the data that we manage at the AODN. So that includes a large part of that is the IMOS data, but there are lots of other data sets in there as well. And so here, all the data are grouped into what we call collections, and each collection has an associated metadata record that describes what's in there and has various keywords associated. So we've got this faceted search. You can look at what physical or what measured parameters. Maybe I can make that a bit bigger. What parameters are in there. And this is a hierarchical thing. So you can look for ocean biota, for example, or various things. There's organizations. If you happen to know what organizations are involved in the data that you collect, that you're interested in, there's different platforms. And then you can also search by just plain text, or full text search, or a bounding box, and so on. And then you can select each of these collections. So for example, we could try and find the one with the profiles that I used in the example. So that is from, well, we know it had physical parameters, temperature in it, for example, or maybe temperature is too broad. Let's pick salinity, if I can find it. Salinity. Okay, so for example, you see there's Argo profiles in there. There's some things collected off ships. And there's the CTD profiles that I used as an example. And so then you can look at where the data are in this collection, and you can actually define a subset here and go to a download where you can actually download data. So this is more the old school way. If you just want a small subset and you just want to work with it locally, you can do that. And in this case, the download actually gives you options to, you can just remember my password, let's hope. You can, in this case, you can download the original data files that are still stored in NetCDFs. But because these are relatively small, it's just profiles. They're essentially one-dimensional. We've actually also pulled them all into a database, and we can serve them up so that you can get them in CSV format. And that's actually what's behind that is the WFS that we were querying directly. Now, if you wanted to, so this is a manual interacting with a web interface way. But if you wanted to we're actually still working your code but find those links, what you can do is view the metadata record for a collection, which you can do from each of these steps. And so this now takes you to our metadata catalog, which is, again, you can use this as a tool to browse all the metadata items that are there, or records that are there, and the ones that are associated with these collections will have these links in them. And in particular, you can see here, we'll make that bigger as well. There's actually two. There's a WMS, a web map service. That's the one I mentioned just at the end, which is used for the map tiles that we see here. So these red triangles are basically the way we rendered this map to preview on here, and that's provided by this web map service, and that's so that's this one. So you can see here's that link to that GeoServer. That's the one we accessed before. Well, there's the WFS one. And unfortunately, this one doesn't actually show. Oh yeah, no, there it is. Sorry. Yeah, so it's a little bit in two parts because it's got the link to the server. So that's the one that we had. Where's that top? Where's that? Yeah, so that's the address here for the server, and then it's got the name of the the feature type here, and that's the one that that we put in here. Except, yeah, for some reason it's missing this prefix for IMOS, but you'll see they all have that. So you just add that on, and that's the one, and that's how, yeah. So that's how you find the associated web feature service link. And then a lot of them will also have a link to threads. In this case, it's got specific, one. So, I didn't mention. Well, we used threads to access the opened app service basically, but threads is this basic catalog which shows all these files that are present for a particular site. And then if we go into one of these and click on the opened app link, then we're back to one of what we talked to in the notebook. Basically, you just copy this data URL here, and you're away. So it's it allows you to browse. So these links where in the metadata record to a threads catalog that takes you there, and then it's a few more clicks to actually find the file that you want. But there it is.